Now, in the last video, we talked about the empirical rule, which is a rule that's used a lot in statistics, but it only applies to bell-shaped distributions. And again, we do have a lot of distributions that are naturally bell-shaped. For instance, heights and weights are typically naturally bell-shaped distributions, so we can use that there. But not every distribution has that bell shape, right? We've seen other examples in class, such as like the uniform distribution, that does not fit that criteria. So there's another theorem that we can use instead, and it's listed right here. And it's not as strong as a relationship, but it still does a really good job kind of getting us in the ballpark of how much data is in between the different standard deviations. So the portion, excuse me, of any data set lying within k standard deviations of the mean is at least this amount. So key here is at least. So with the empirical rule, we kind of had more exact percents, maybe rounded, but pretty close, where here we're using the word at least. So you know that that's your minimum. So for instance, if k is equal to 2, which is pretty standard, so this is 2 standard deviations, then our formula gives us 1 minus 1 over 2 squared. And of course, 1 over 2 squared is 1 over 4. So when we take 1 whole and subtract a fourth from it, we get 3/4 left over, which is 75%. So in any data set, at least 75% of the data will lie within 2 standard deviations of the mean. Now, it could be more than 75%. We're not saying it's exactly, but that would be the minimum. So you're still seeing that the majority of your data is within 2 standard deviations of that mean. If k equals 3, so 3 standard deviations, well, we have 1 over 3 squared as the part in our formula, and 3 squared is 9. So we take 1 whole and we subtract 1/9, we're left with 8/9. That's about 88.9%. So again, at least 88.9% of the data lie within 3 standard deviations of the mean, and that's with any distribution, which is really great, right? So it doesn't have to be that bell-shaped, that normal distribution. So let's look at an example. It says the age distributions for Georgia and Iowa are shown in the histograms. So this is for Georgia, this is Iowa. It's not exactly, but it does look like a lot of this data is relatively uniform, right? Particularly on the left side. Once you get into older ages, not as much, but it's definitely not a bell-shaped curve. And what they want us to do is apply the theorem to the data for Georgia using k equals 2. So we're talking about 2 standard deviations here. Now, we already saw that when k is equal to 2, this means that at least 75% of the data lie within 2 standard deviations of the mean. Okay, so it's always 75%. If k is 2, it's always 75%. If k is 3, it's always 88.9%. So let's focus on Georgia here. And we want to know also, is the age of 100 unusual? So not just guessing, but actually mathematically, are we seeing that this is an unusual data point, meaning that it lies outside those 2 standard deviations? So remember, unusual is typically outside 2 standard deviations. I'm just going to abbreviate there from the mean. Okay. So I have my data, I have my mean, and I have my sigma, which is my standard deviation for the population. And the first thing I'm going to do is actually figure out what these cutoff values are. So we know our mean is 37.3 years, and my standard deviation is 22.3 years. So I'm looking for this range. So what I need to find first is the mean minus 2 standard deviations. So I'm going to take that 37.3 and subtract that 22.3 twice. So what I can do is multiply that by 2. And I also want to find my mean plus 2 standard deviations. So I'm going to add that 22.3 twice, or again, I can multiply by 2 here. And let's see, when you do those calculations, you should get negative 7.3 and positive 81.9. Now, in this particular example, it doesn't make sense to have a negative age. So what we would do here is use the age of 0, right? Because it doesn't make sense to be negative. We're not going to be negative years old. So we would make that 0, makes more sense. So at least 75% of the population is between 0 and 81.9 years old. So that's what this theorem is telling us. So it's giving us our cutoff for at least 75% of the population. So the majority of people in Georgia are between 0 and 81.9 years old. So someone who is 100 years old is outside this range. And so this would be unusual. Okay? Because it's beyond the 2 standard deviations. If it was beyond 3 standard deviation, it would be considered very unusual. But again, typically those 2 standard deviations tend to be our cutoffs for what is usual versus unusual.